Right, the first thing I should clear up from the first part of the video, the sign diagrams, whilst they were technically correct, they're not really correct in the kinematics context, because as I've drawn a line through here, zeros, if you think about what we're dealing with the velocity function for a given time and the acceleration function for a given time of a moving particle. So basically negative numbers don't exist in the domain. So time starts at 0, so you kind of need to chop off the graphs here. Just effectively, this bit doesn't need to exist. So the velocity, what we're going to use from now, the velocity is going to be negative. This is at 0, so it's going to be negative to begin with, which means it's moving to the left, as we've already discussed with the initial conditions. And then after 1 second, it's positive, which means it's moving right. So basically this point here, the 0 on velocity, is when the thing turns around, so that the thing, it goes this way for a second and then it goes back again. Yes, it's all on one line, it kind of goes, and then it will just keep going forevermore. The acceleration function then, once we've chopped this bit off, there's no negative acceleration, so all the time, even though at the beginning this thing's moving to the left, it's being kind of dragged, it's slowing down that way, being dragged off towards the right. So describe the motion of the particle at t equals 2. So at t equals 2 seconds. So we're going to need S2 which is 2 cubed minus 3 times 2 plus 1 equals 8, minus 6 plus 1, well 8 minus 6 is 2, 2 plus 1 is 3, so it's 3 cm. So it would be 3 centimeters to the right in position. The acceleration, sorry, the velocity v2 equals, what was the velocity function? 3t squared minus 3, so that would be 2 squared minus 3, or 2 squared is 4, 3 4 is 12, 12 minus 3 equals 9 meters per second minus 1, so that is positive, which means it's pushing the thing that way, so it's just speeding up. And A2, I'm going to need a new board for A2, I have a new board. A2 equals the acceleration function is, it was 6t, so it's 6 times 2 equals 12 centimeters per second squared, which probably means this is also centimeters per second minus 1. So what does that mean in terms of the motion? So put it all together. So after 2, at t equals 2, the particle is 3 centimeters to the right of the origin, so it is travelling at 9 centimeters per second towards the right, and it is accelerating at 12 centimeters per second squared. So it just means it's increasing. Right, part D is asking us to find the position of the particle when changes in direction occur, right? So I've actually already spoken about that. Perhaps if I just move this one to one side. So you know for your velocity sign diagram, so if we chop it, you've got this 0 at 1, so you had a negative velocity yet and positive. So if you think, imagine you're the particle, negative velocity means you're moving, it only moves along a straight line, it means it's moving to the left. A 0 is when it's not moving at all, and positive means it's moving towards the right. So at this point, particle changes direction. At t equals 1s. And it's asked us to find the position of the particle, so we need to find S1. So that would be 1 cubed minus 3 times 1 plus 1. So 1 cubed is 1. 3 times 1 is 3, so 1 minus 3 is minus 2 plus 1 minus 1 cm. Okay, so it changes direction. When particle is 1 cm left of origin. Okay, we're getting there very slowly. Right, so now part E is asking us to draw a motion diagram, right? So you know that T0 equals, I've written that down somewhere, even 1. Right, so you know if I draw this as the line, it's at 1, the particle is going to be here at t equals 1, so t equals 0. Going to be around there. I might make a note of that there and then possibly move it. So you know after 1 second the particle is 1 centimetre to the left, and that's when a change happens. So if I go 0 minus at -1, this is when the thing turns around. So it's basically going from here and it's going to turn around. Now if you're drawing a straight line of motion, if you kind of draw it like that and then change direction and go like that, which is what the particle actually does, it's not going to look great on a diagram. So the way you draw it instead, you kind of draw the backwards journey like this and you kind of swap around like that. Okay, so did we have any other useful information? So we knew that S2 equals 3. So I know at 2 seconds S is 3 and it goes to here after 1. So you're sort of getting a picture of the journey now. So you know it's here at t equals 0. So I'm just, as I said, I might move that. See if I can fit that in here. At t equals 0. T equals 2. It's here. And here, when it changed direction, that happened after 1 second, I think, wasn't it? Yeah, 1 second in here. So this is at t equals 1. So you're kind of getting an idea for the motion of the particle. So it goes this way and then it changes direction and it starts to go this way and it doesn't stop. Okay. Part F. For what time interval is the particle speed increasing? Now I've seen a lot of people get this wrong, so this one actually doesn't affect it, but basically there are 2 ways a particle can be increasing speed. So it could be when it's going this way, so if it's travelling to the left with a negative acceleration, so if the acceleration is pushing it to the left and it's already travelling to the left, then if you were that particle, you're getting faster, so you're speeding up, but in that direction. And obviously if you're going to the right, if you've got a positive velocity and a positive acceleration, you're going along this line and you're speeding up as you do it, right? So basically, whenever velocity and acceleration have the same sign, that is when the thing is speeding up. If I can just go back to this. back to the sine diagram, you don't have a situation where they're both negative, because acceleration is actually never negative, so it happens in here. If those diagrams continue, they're just going to keep going on forever. So at 1 second they start to have the same sign, so, or just after 1, I guess. So when t is greater than or equal to 1, particle is accelerated. Now you might be thinking, why is he including the 1? And it just goes back to when you talk about when is a function increasing, you include the 0 in that. It's the same thing because it's talking about an interval. But technically, yes, it's not actually accelerating when t equals 1, but it's about the interval. And is there one more part to this huge question? What is the total distance travelled from t equals 0 to t equals 2? So total distance. So fortunately, this is part G, right? Fortunately, I haven't rubbed this out yet, so I still have this diagram. So it starts at 1, it goes to -1, so that's 2 centimeters, so it does 2 centimeters, that goes left, plus, and then it moves from here 1, 2, 3, 4, so it goes from -1 to 3, so it goes plus 4 centimeters that way. I'm smudging left-hander's curse to the right. 2 plus 4 is 6 centimeters travelled. And it does actually say in the book, we will be doing this sort of thing with integration later in the course. You'll be integrating a function. But right now, if you can understand this particle motion, get an idea for the sine diagram, the changes of sign, when the thing's increasing speed, could happen in 2 ways. It could happen this way or this way. If you can draw the motion diagram, work out things like that, you'll be in a very good position, certainly for this week.